Hello there. I'm glad you're here tonight. Tonight, we're going to journey together through one of those questions that seems simple until you really think about it. What is gravity? Really? You've lived with it every moment of your life, felt its gentle tug with every step, every breath, every blink. Yet gravity remains one of the most beautiful puzzles in all of science. A force so familiar we barely notice it, yet so profound that understanding it has reshaped how we see reality itself. Before we get into it, I would like to know where you're watching this video and what's your time now, wherever you might be watching from. Perhaps you're tucked into bed, maybe settling into a favorite chair, or finding a quiet moment as the world winds down around you. How fitting that you've chosen to explore one of the universe's most fundamental mysteries. Gravity, at this peaceful hour when gravity itself is gently pulling you toward rest. Now, let's begin. Have you ever stood at the edge of a tall building and felt that peculiar sensation in your stomach? That mix of fear and fascination, as you imagine what it would be like to step into empty air. We call it the pull of gravity, don't we? That invisible hand, reaching up from the earth, tugging at everything, drawing it down, down, down toward the center of our world. But here's something wonderful and strange, that feeling you have, that sense of weight pressing you into your chair or bed right now, isn't actually gravity pulling you down. It's something far more beautiful and mysterious than that. Imagine, if you will, that you're not sitting still at all. Imagine that you're actually falling right now, this very moment, through space and time, following the most natural path possible through the universe. But the ground beneath you, the chair you're sitting in, the bed you're lying on, they're all pushing up against you, interfering with your natural fall through the curved landscape of space-time itself. This is Einstein's gentle revolution, whispered to us more than a century ago. Gravity isn't a force pulling you down, it's the shape of space and time itself, curved and bent by the presence of mass and energy. You're not being pulled toward the Earth. You're following the straightest possible path through a universe that's been gently warped by our planet's presence. Think of it like this. Imagine you're walking across a vast trampoline, perfectly flat and tight. Your steps are straight and true. But now, imagine someone places a heavy bowling ball in the center of that trampoline. The fabric dips and curves, creating hills and valleys in what was once flat. Now, when you try to walk in a straight line, you find yourself naturally rolling toward the bowling ball, not because it's pulling you, but because the very surface you're walking on has been reshaped. This is what mass does to space-time. The sun doesn't pull the planets toward it. It curves the fabric of space-time so dramatically that planets, following their natural straight-line paths, end up orbiting in great sweeping circles. The Earth doesn't pull the moon toward it. It creates a gentle depression in space-time that the moon rolls around, like a marble circling the rim of a funnel. And you, right now, are following that same natural path, falling freely through Einstein's curved universe. It's only the solid matter beneath you that creates the sensation of weight, pushing up against your natural trajectory through space-time. In a way, you're always falling, and the ground is always catching you, moment by moment, creating that familiar feeling of being pressed down that we call weight. Isn't it wonderful? The most fundamental experience of your physical existence, the feeling of gravity, is actually the universe's way of showing you that space and time themselves are alive, flexible, responsive to the presence of matter and energy. Every step you take, every breath you breathe, every moment you spend resting here, you're participating in a cosmic dance between matter and the very fabric of reality itself. There's something almost magical about satellites, isn't there? Those tiny points of light that sometimes catch your eye as they drift silently across the night sky, moving with such purpose and grace. Children often ask how they stay up there. And the answer we usually give, that they're held by gravity, only scratches the surface of something far more poetic and profound. Here's the beautiful secret. Satellites aren't really staying up at all. They're falling, just like everything else. But they're falling sideways so perfectly that they keep missing the ground. Imagine you're standing on a very tall mountain, taller than any mountain that actually exists, so tall that you can see the curve of the earth below you. Now imagine throwing a ball as hard as you can toward the horizon. The ball flies out, following a graceful arc, and eventually falls to earth some distance away. But what if you could throw it harder? Much harder. Throw it hard enough, and something wonderful happens. The ball flies out toward the horizon. But by the time it would normally fall to Earth, the Earth itself has curved away beneath it. The ball keeps falling, but the ground keeps curving away, and the ball never quite catches up. It falls all the way around the Earth, completing a great circle, and comes back to you, still falling, still trying to reach the ground that's always just out of reach. This is orbit, the art of falling sideways with such precision that you never hit what you're falling toward. The International Space Station, that bright dot that sometimes passes overhead in the early evening, is falling toward Earth at this very moment. It's falling at thousands of miles per hour, accelerating toward our planet with the same desperate urgency as any dropped stone. It's also moving sideways so quickly that Earth's surface curves away beneath it at exactly the same rate it's falling downward. The astronauts inside aren't floating because there's no gravity up there. They're floating because they're in free fall, just like you would be if you jumped off a cliff. Except their fall never ends. They're falling in perfect unison with their spacecraft. So from their perspective, they're weightless, drifting like leaves in a gentle breeze. It's the same story with the moon. Our faithful companion isn't hanging in the sky by some cosmic string. It's falling toward Earth, has been falling toward Earth for billions of years. But it's falling sideways so perfectly that it traces out that familiar circle in our sky, month after month, year after year. The moon is locked in an eternal dance of falling and missing, caught in the sweet spot between escape and collision. And the Earth itself, we're falling too, falling around the sun at tens of thousands of miles per hour, following the curved path that the sun's mass has carved into space-time. We're all falling together. Earth, moon, satellites, space stations, even the occasional asteroid that wanders too close. All of us following the invisible highways that mass and energy have drawn through the landscape of space-time. There's something deeply comforting about this, isn't there? The idea that we're all falling together, that the very stability of our world depends on this precise eternal dance of falling and missing. The moon won't suddenly drop out of the sky, not because it's held up by some mysterious force, but because it's falling so perfectly that it can never quite reach us. The Earth won't spiral into the sun, not because something is holding us back, but because we're falling sideways with such exquisite precision that we trace out the same elliptical path year after year. We live in a universe of perpetual falling, where stability comes not from staying still, but from moving with such grace and precision that we never quite land where we're falling toward. Every satellite overhead, every planet in our solar system, every star orbiting the galactic center, all of us are falling together through Einstein's curved spacetime, following the natural paths that mass and energy have laid out for us, like rivers following the contours of a landscape we can barely imagine. Picture, if you will, a young man sitting beneath an apple tree on a warm afternoon in 1666. The story goes that an apple fell, not onto his head, as legend would have it, but simply fell, as apples do, from branch to ground. But this particular fall sparked something extraordinary in the mind of Isaac Newton, something that would change how we understand the universe itself. Newton watched that apple fall and asked a question that seems almost childlike in its simplicity. Why does the apple fall toward the Earth and not the other way around? Why doesn't the Earth fall up toward the apple? And in that moment of wondering, he glimpsed something that no one had seen before, that the same force that draws an apple to the ground also keeps the moon in its orbit and the planets in their paths around the sun. This was revolutionary thinking. For centuries, people had believed that the heavens operated by different rules than the Earth, that celestial bodies moved in perfect circles because they were made of different, more perfect stuff. But Newton saw unity where others saw separation. The apple and the moon, he realized, were both falling toward the Earth, following the same invisible force that reached across empty space to touch everything with mass. He called this force gravity, and described it with mathematical precision that still takes your breath away. Every object in the universe, he said, attracts every other object with a force that depends on their masses and the distance between them. The more massive something is, the stronger its gravitational pull. The farther apart two things are, the weaker the attraction between them. Simple, elegant, and for more than 2 centuries, it explained everything from falling apples to the orbits of comets. But then came Einstein, with his wild hair and his even wilder ideas, and he looked at Newton's beautiful theory, and asked an even deeper question: what if gravity isn't a force at all? Imagine you're in a windowless room, perhaps an elevator, and you feel yourself pressed firmly against the floor. How would you know whether you're standing still in a gravitational field or accelerating upward through empty space? Einstein realized that you couldn't tell the difference, not by any experiment you could perform inside that room. This simple insight, this recognition that gravity and acceleration are fundamentally indistinguishable, led him to a startling conclusion. What if gravity isn't a force pulling things together, but rather a curvature in the fabric of space and time itself? What if mass and energy don't attract each other across empty space, but instead walk the very stage on which all motion takes place? Einstein invited us to imagine spacetime as a flexible sheet, like a stretched rubber membrane. Place a heavy ball in the center, and the sheet dimples and curves around it. Now roll a smaller ball across the sheet, and it won't travel in a straight line. It will follow the curves created by the heavy ball, spiraling inward or orbiting around the depression. This is Einstein's vision of gravity. The sun doesn't pull the planets toward it with some mysterious force. It curves space-time so dramatically that planets, following the straightest possible paths through this curved geometry, end up orbiting in elegant ellipses. The Earth doesn't pull the moon toward it. It creates a gentle depression in space-time that the moon rolls around, like a marble circling the rim of a funnel that never quite reaches the bottom. And that apple that fell in Newton's garden, it wasn't pulled toward the Earth by a force. It was following the most natural path possible through space-time that had been curved by the Earth's presence. The apple fell because that's what objects do in curved space-time. They follow geodesics, the straightest possible paths, through a geometry that's been gently warped by mass and energy. Both visions are beautiful, aren't they? Newton's universe of invisible forces reaching across empty space, binding everything together with mathematical precision. Einstein's universe of curved space-time, where gravity becomes geometry, where the stage itself participates in the dance of matter and energy. Newton's apple fell because the Earth called to it across the void. Einstein's apple fell because it was following the natural contours of a space-time curved by the Earth's presence. Same apple, same fall, but two completely different stories about what it means to move through the universe. And the remarkable thing is, both stories work. For everyday purposes, for calculating orbits and predicting tides, Newton's force-based picture is perfectly adequate. But when you want to understand the deeper nature of gravity, when you want to explore black holes or the expansion of the universe, you need Einstein's curved space-time. It's not that Newton was wrong, it's that he was telling a simpler story about something infinitely more complex and beautiful. The apple still falls, the moon still orbits, the planets still dance around the sun, but now we know that they're not being pulled by invisible strings. They're surfing the curves of space-time itself, following the geometric paths that mass and energy have carved into the very fabric of reality. Close your eyes for a moment and try to imagine something impossible. A fourth dimension of space, not time. That's different. But an actual fourth direction you could move in, perpendicular to up, down, left, right, and forward, backward. Can you picture it? Of course not. Our brains, shaped by evolution in a three-dimensional world, simply can't visualize four-dimensional space. But here's something wonderful. Even though we can't see it, we can feel it. Every time you drop something, every time you feel your weight pressing down, every time you watch the moon trace its path across the sky, you're experiencing the effects of four-dimensional geometry. You're feeling the curvature of space-time itself. Einstein showed us that space and time aren't separate things. They're woven together into a single fabric, a four-dimensional landscape that can be stretched and bent and curved by the presence of mass and energy. And when this fabric curves, we experience that curvature as gravity. Think about this. When you're walking on flat ground, you move in straight lines. But imagine you're walking on the surface of a giant sphere, like the Earth. You think you're walking straight, but from a higher perspective, you're actually following a curved path. The curve of the Earth's surface. The geometry of the surface you're walking on determines the paths you can take. This is exactly what happens with gravity. Except the surface is four-dimensional space-time, and instead of walking on it, you're moving through it. The sun's mass curves space-time around it, creating hills and valleys in this four-dimensional landscape. The Earth, moving through this curved space-time, follows what feels like a straight line from its own perspective. But from our higher dimensional viewpoint, it's actually following a curved path, an elliptical orbit around the sun. Here's where it gets beautifully strange. The curvature isn't just in the space dimensions, it's in time as well. Mass doesn't just curve space, it curves time. And when time is curved, clocks run at different rates depending on where they are in the gravitational field. Imagine space-time as a vast landscape of rolling hills and deep valleys. Where the landscape is flat, time flows at its normal rate, but near massive objects, space-time dips and curves, creating what we might call gravitational valleys. And in these valleys, time runs slower. This isn't just theoretical, it's measurable, practical, and happens all around us. Your head, being slightly farther from the Earth's center than your feet, experiences time passing infinitesimally faster than your feet do. The difference is unimaginably small, billionths of a second over a lifetime, but it's real and measurable, with precise enough instruments. GPS satellites orbiting high above the Earth experience this effect dramatically. They're farther from Earth's gravitational well, so time runs faster for them than it does for us down here on the surface. Without corrections for this relativistic effect, GPS would accumulate errors of several miles per day. Every time you use your phone to navigate, you're relying on corrections for the curvature of space-time. But what does it actually mean for space-time to be curved? Here's an analogy that might help. Imagine you're an ant, living on the surface of a perfectly flat piece of paper. From your ant's perspective, the shortest distance between 2 points is a straight line. But now imagine someone gently bends the paper, creating hills and valleys. You're still constrained to move along the surface. But now, the shortest path between 2 points isn't a straight line in the larger space, it's a curved path that follows the contours of the bent paper. This is what massive objects do to space-time. They bend it, creating geometric landscapes that determine how everything else moves. Objects don't fall toward massive bodies because they're being pulled. They follow the straightest possible paths through curved space-time, and those paths happen to lead toward the massive objects that created the curvature in the first place. It's as if the universe is a vast, multi-dimensional landscape, and mass and energy are like heavy objects placed on this landscape, creating dips and curves and valleys. Everything else, planets, stars, light rays, even particles of matter, moves through this landscape like water flowing downhill, following the natural contours that mass and energy have carved into the geometry of space-time itself. The remarkable thing is that this curvature isn't just a mathematical abstraction, it's physically real. Space-time has a shape, a geometry that can be measured and mapped. And that shape, that curvature is what we experience as gravity. When you feel your weight pressing down, when you watch an apple fall, when you see the moon overhead, you're experiencing the four-dimensional geometry of the universe itself. Have you ever noticed how time seems to behave differently in different places? How a lazy summer afternoon can stretch on forever, while an exciting evening passes in the blink of an eye? We usually think of this as psychological, our perception of time changing, based on our emotional state or level of engagement. But there's something deeper happening here, something that reaches right into the fundamental nature of time itself. Einstein discovered something that sounds like science fiction but is absolutely, measurably real. Time doesn't flow at the same rate everywhere in the universe. The rate at which time passes depends on where you are in a gravitational field. The deeper you are in a gravitational well, the closer you are to a massive object, the slower time runs for you compared to someone higher up. This isn't just a theoretical curiosity, it's happening to you right now. As you read these words, time is running slightly slower for your feet than for your head. The difference is unimaginably small, billionths of a second over a lifetime. But it's real and measurable, with precise enough instruments. Your feet are closer to the Earth's center, deeper in the gravitational well, so they experience time at a slightly slower rate than your head. Picture this. Imagine you and a friend are standing at the base of a very tall tower. You stay at the bottom while your friend climbs to the top. You both have identical, perfectly synchronized clocks. Now you wait. Hours pass. Days pass. Years pass. When your friend finally comes back down, you compare your clocks and discover something astonishing. Your friend's clock is running slightly ahead of yours. Your friend, farther from the Earth's center, has experienced time passing slightly faster than you have. This effect, called gravitational time dilation, becomes more dramatic the stronger the gravitational field. On the surface of the Sun, time runs about 2 parts per million slower than it does here on Earth. Near a black hole, the effect becomes extreme. Time crawls to a near standstill for someone falling toward the event horizon, at least from the perspective of someone watching from far away. But here's what's truly beautiful about this. It's not that gravity somehow interferes with clocks or slows down physical processes. It's that gravity literally curves time itself. Time, as it turns out, is not the absolute universal constant we once thought it was. It's flexible, malleable, responsive to the presence of mass and energy. Think of it this way. Imagine spacetime as a vast landscape of rolling hills and deep valleys. Time flows like a river through this landscape, and just as a river flows more slowly through flat meadows and more quickly down steep hillsides, time flows at different rates depending on the local curvature of spacetime. The GPS satellites orbiting high above us experience this effect every day. They're farther from Earth's gravitational well, so time runs faster for them than it does for us down here on the surface. Without corrections for this relativistic effect, GPS would accumulate errors of several miles per day. Every time you use your phone to find your way somewhere, you're relying on corrections for the curvature of time itself. But the implications go far beyond practical applications. This malleability of time hints at something profound about the nature of reality itself. Time isn't just the stage on which events unfold, it's an active participant in the cosmic drama, shaped by mass and energy, curved by the presence of matter. Imagine you're standing at the edge of a black hole, not close enough to fall in, but close enough to feel its immense gravitational pull. You drop a clock toward the black hole, and watch it fall. As it gets closer to the event horizon, something strange happens. The clock appears to slow down, its hands moving more and more sluggishly. The clock's final tick, before crossing the event horizon, seems to stretch out forever, frozen in time from your perspective. This isn't an optical illusion from your vantage point. Time really is running slower for the falling clock. The clock experiences its own time normally, 1 second per second. But from your perspective, watching from a safe distance, that second stretches out longer and longer as the clock approaches the event horizon. This is the strange democracy of time in Einstein's universe. Everyone experiences their own time normally, but time itself is relative, flowing at different rates for different observers depending on their position in the gravitational landscape of space-time. It makes you wonder, doesn't it? As you lie here, perhaps feeling sleepy, perhaps feeling time slow down in that pleasant way it does when you're drifting towards sleep. You're participating in something cosmic. The time you experience, the rate at which your thoughts unfold, the rhythm of your heartbeat, all of it is shaped by your position in the curved geometry of space-time itself. You're not just resting in space, you're resting in time, floating in the gentle currents of temporality that flow through the gravitational landscape of our universe. And that landscape, shaped by the mass of the Earth beneath you, the sun above you, and all the distant stars, is quietly determining the rate at which this moment unfolds, the pace at which your thoughts drift, the rhythm of your journey towards sleep. There's something almost rebellious about Einstein's approach to gravity, isn't there? For centuries, gravity had been understood as a force invisible, mysterious, but undeniably real. It was the cosmic glue that held the universe together, the invisible hand that guided planets in their orbits and kept our feet firmly planted on the ground. And then along came Einstein with his wild hair and his even wilder ideas. And he essentially said, what if gravity isn't a force at all? It's a bit like someone looking at a rainbow and saying, what if that's not actually made of colored light? The audacity of it, the willingness to question something so fundamental that everyone else took for granted, that's the mark of a truly revolutionary mind. But Einstein didn't just make this claim out of thin air. He arrived at it through a series of thought experiments that are beautiful in their simplicity. Imagine you're in a windowless elevator, and you feel yourself pressed firmly against the floor. How would you know whether you're standing still in a gravitational field, or accelerating upward through empty space at a constant rate? Einstein realized that you couldn't tell the difference, not by any experiment you could perform inside that elevator. This simple insight, this recognition that gravity and acceleration are fundamentally indistinguishable, led him to a startling conclusion. What if gravity isn't a force pulling things together but rather a manifestation of the curvature of space-time itself? What if objects don't fall because they're being pulled, but because they're following the straightest possible paths through a curved four-dimensional landscape? Think about it this way. If you're walking on a flat surface, you naturally move in straight lines. But if you're walking on a curved surface, the surface of the Earth, for example, your straight paths are actually curved from a higher dimensional perspective. You're not being pulled along curved paths. You're following the natural geometry of the surface you're walking on. This is exactly what Einstein proposed for gravity. Objects don't fall toward massive bodies because they're being pulled by a force. They follow the straightest possible paths through spacetime that has been curved by the presence of mass and energy. A falling apple isn't being pulled toward the Earth. It's following a geodesic, the four-dimensional equivalent of a straight line through curved spacetime. This reframing of gravity has profound implications. In Newton's universe, gravity was something that happened to objects, a force that acted upon them from the outside. In Einstein's universe, gravity is something that emerges from the very structure of space-time itself. It's not something that acts upon objects, it's the stage on which all motion takes place. Consider an astronaut floating in the International Space Station. From Newton's perspective, the astronaut is still under the influence of Earth's gravitational force, but that force is balanced by the centrifugal force of orbital motion. From Einstein's perspective, the astronaut is simply following a natural path through curved space-time, a path that happens to be a closed orbit around the Earth. The astronaut isn't being pulled or pushed by any forces, they're in free fall, following the geometry of space-time itself. This is why astronauts feel weightless. They're not beyond the reach of gravity, they're in the purest possible manifestation of gravity. They're following the natural contours of curved space-time without any other forces interfering. Weight, it turns out, isn't caused by gravity. It's caused by forces that prevent you from following your natural gravitational path. The ground pushing up against your feet, the chair supporting your body. These are the forces that create the sensation of weight by preventing you from free-falling through curved spacetime. It's a complete inversion of our intuitive understanding. We think of gravity as the force that creates weight, but in Einstein's universe, gravity is actually the absence of force, the natural, unimpeded motion through curved spacetime. Weight is what happens when something interferes with that natural motion. This reconceptualization of gravity has led to some of the most profound discoveries in modern physics. Black holes, gravitational waves, the expansion of the universe, all of these phenomena emerge naturally from Einstein's geometric understanding of gravity. They're not the result of mysterious forces acting across empty space. They're the inevitable consequences of mass and energy curving the fabric of space-time itself. But perhaps the most beautiful aspect of this revolution is how it changes our relationship with the universe. In Newton's world, we were passive objects acted upon by forces. In Einstein's world, we're active participants in the geometry of space-time. Every step you take, every breath you breathe, every moment you spend resting here, you're not just moving through space and time, you're moving through space-time, following the natural paths that mass and energy have carved into the very fabric of reality. You're not being pulled toward the Earth by a mysterious force. You're following the straightest possible path through a four-dimensional landscape that has been gently curved by the Earth's presence. And that path, that natural geodesic through curved space-time, is what we experience as the familiar, comforting sensation of gravity, keeping us grounded, keeping us connected to our planetary home. There's a moment in every amateur astronomer's journey when they first point their telescope at a distant galaxy and realize something profound. The light entering their eye has been traveling through space for millions or billions of years. That photon began its journey when the universe was younger, when the solar system was just forming, when life on Earth was taking its first tentative steps toward complexity. And now, at the end of its impossibly long journey, it's reaching your retina, carrying information across vast gulfs of space and time. But here's something even more remarkable. That light hasn't traveled in a straight line. It's been curved, bent, and sometimes even split into multiple images by the gravitational fields of massive objects along its path. Gravity, it turns out, doesn't just affect matter, it affects light itself, bending the very fabric of space-time through which light must travel. This phenomenon, called gravitational lensing, turns massive objects into cosmic magnifying glasses. When light from a distant galaxy passes near a massive cluster of galaxies, the cluster's gravity bends the light's path, sometimes creating multiple images of the same distant galaxy, sometimes stretching it into beautiful arcs and rings that astronomers call Einstein rings. Imagine you're looking at a distant candle flame through a wine glass. The curved glass distorts the image, perhaps creating multiple images of the same flame, perhaps stretching it into strange shapes. This is exactly what happens when light from distant galaxies passes through the gravitational field of massive objects. The curved spacetime acts like a lens, bending and focusing the light in ways that can create spectacular cosmic mirages. Some of the most beautiful images from the Hubble Space Telescope show these gravitational lensing effects. You'll see a massive galaxy cluster in the foreground, surrounded by dozens of thin, arc-like streaks of light. Each of those streaks is actually a distant galaxy, its light stretched and magnified by the gravitational field of the cluster. It's as if the universe is using massive objects as natural telescopes, allowing us to see galaxies that would otherwise be too faint and distant to observe. But gravitational lensing isn't just beautiful, it's also incredibly useful. By studying how light is bent by massive objects, astronomers can map the distribution of mass in the universe, including the mysterious dark matter that makes up most of the cosmos. They can measure the distances to faraway galaxies, study the expansion of the universe, and even detect planets orbiting other stars. The effect is so precise that astronomers can use it to weigh entire galaxies and galaxy clusters. The amount of lensing depends on the mass of the lensing object, so by measuring how much a distant galaxy's image is distorted, astronomers can determine how much mass is doing the distorting. It's like weighing the universe one galaxy at a time, using light itself as a cosmic scale. Sometimes the lensing effect is so strong that it creates what astronomers call a gravitational telescope, a massive object that acts like a natural magnifying glass, allowing us to see objects that would otherwise be completely invisible. Some of the most distant galaxies ever observed have been discovered this way, their light magnified by the gravitational field of closer objects. There's something deeply poetic about this, isn't there? The universe is full of natural lenses, cosmic magnifying glasses that allow us to see deeper into space and further back in time than would otherwise be possible. Every massive object, every galaxy, every cluster of galaxies, every black hole is potentially a window into the most distant reaches of the cosmos. And it's all because gravity doesn't just affect matter, it affects the very geometry of space-time itself. Light doesn't choose to curve around massive objects. It follows the straightest possible path through curved space-time. From the light's perspective, it's traveling in a perfectly straight line. It's only from our perspective, embedded in the same curved space-time, that we see the light's path as bent. This is one of the most beautiful confirmations of Einstein's vision of gravity. Light has no mass, so in Newton's universe, it shouldn't be affected by gravity at all. But in Einstein's universe, gravity isn't a force acting on massive objects, it's the curvature of space-time itself. And since light must travel through space-time, it's inevitably affected by any curvature in that space-time. Every time you see a gravitational lensing image, you're seeing direct evidence that space-time is curved, that massive objects bend the fabric of reality itself. You're seeing the universe use its own geometry as a tool for exploration, turning gravity into a cosmic microscope that reveals the deepest secrets of space and time. As you rest here, perhaps feeling drowsy, remember that light from distant galaxies is constantly being bent and curved by gravity as it travels through the universe. Some of that light might be on its way to Earth right now, carrying information about galaxies so distant that their light began its journey when the universe was just a fraction of its current age. And that light, curved by the gravitational lenses of the cosmos, will eventually reach our telescopes, bringing us messages from the deepest reaches of space and time. There's something wonderfully counterintuitive about the International Space Station, that bright dot that occasionally graces our evening sky. The astronauts inside appear to float effortlessly, bouncing off walls, doing somersaults in mid-air, handling droplets of water that form perfect spheres and drift through the cabin like tiny planets. We say they're weightless, that they've escaped Earth's gravity, but that's not quite right. The truth is far more beautiful and strange. The astronauts aren't beyond gravity's reach at all. They're actually falling toward Earth, have been falling continuously since the moment they reached orbit, and will continue falling for as long as they remain in space. They're experiencing the purest form of gravity possible, unimpeded free fall through curved space-time. Think about it this way. If you were in a windowless elevator and the cables suddenly snapped, you would feel weightless during your fall. You and the elevator would accelerate downward together, and from your perspective inside the elevator, you'd float freely, just like the astronauts. The only difference is that the space station is falling sideways so fast that it keeps missing the Earth. This is the secret of orbital mechanics, the elegant dance between falling and missing that keeps satellites in space and planets in their orbits. The space station is traveling at about 17,500 miles per hour, fast enough that by the time it would normally fall to Earth, the Earth's surface has curved away beneath it. It's locked in a perpetual state of falling and missing, tracing a great circle around our planet. The astronauts inside are experiencing what physicists call microgravity, Not the absence of gravity, but the presence of gravity without any other forces to interfere with it. They're following their natural path through curved spacetime, unimpeded by floors or chairs or any solid surface pushing up against them. It's a pure state of being in a way. Down here on Earth, we never experience gravity directly. What we feel as weight is actually the electromagnetic force, the force that keeps atoms from passing through each other, preventing us from following our natural gravitational path. The ground pushes up against our feet, chairs push up against our bodies, and we interpret this constant upward push as the downward pull of gravity. But the astronauts are free from all of that. They're experiencing gravity as Einstein envisioned it, not as a force but as the natural curvature of space-time. They're following geodesics, the straightest possible paths through four-dimensional space-time, and those paths happen to be closed orbits around the Earth. There's something deeply peaceful about this image, isn't there? The idea of floating freely through space, following the natural contours of curved space-time, free from the constant push and pull of solid surfaces. It's perhaps the closest thing to pure motion that human beings can experience. Movement guided only by the geometry of the universe itself. And it's not just the astronauts who experience this. Every satellite, every piece of space debris, every drop of water released from the space station, they're all in the same state of perpetual free fall, all following their natural paths through the gravitational landscape of space-time. Sometimes astronauts describe the experience of looking down at Earth from this state of weightlessness. They see our planet turning slowly beneath them, a blue marble suspended in the black void, and they realize viscerally that they're not separate from it. They're part of it, falling with it through space, sharing the same gravitational relationship with the sun and moon and all the other bodies in the solar system. From their perspective, Earth isn't pulling them down. They're simply following parallel paths through curved space-time, paths that happen to circle around our planet. They're not fighting against gravity, they're dancing with it, following the natural choreography that mass and energy have written into the fabric of space-time itself. This state of weightlessness reveals something profound about the nature of gravity. It shows us that gravity isn't really a force at all. It's the baseline condition of the universe, the natural state of motion through curved space-time. Weight, the sensation of being pulled downward, is actually what happens when something interferes with that natural motion. You right now are not at rest. You're accelerating upward at about 32 feet per second squared, pushed by the electromagnetic forces that keep you from falling through the solid matter beneath you. The astronauts floating freely in their space station are the ones who are truly at rest, following the natural paths that gravity has carved into the geometry of space-time. It's a complete inversion of our everyday understanding, but it reveals something beautiful about the universe we live in. We're not passive objects being pulled around by mysterious forces. We're active participants in a cosmic dance, following the natural contours of a space-time curved by mass and energy, pushed and pulled by the fundamental forces of nature. All of us together tracing out the grand patterns of motion that govern everything from falling apples to orbiting planets to the expansion of the universe itself. Step outside on a clear night and look up at the stars. Each point of light you see is a sun, many of them far larger and more massive than our own, scattered across distances so vast that their light takes years or decades or centuries to reach your eyes. But the stars you can see with the naked eye are just the closest neighbors in our cosmic neighborhood, a tiny fraction of the hundreds of billions of stars that make up our galaxy, the Milky Way. And our galaxy itself is just one of hundreds of billions of galaxies, scattered throughout the observable universe, each containing hundreds of billions of stars, all of them bound together by the gentle but inexorable pull of gravity. It's gravity that holds these vast collections of stars together, gravity that shapes the large-scale structure of the universe itself. But here's what's truly remarkable. If you could somehow step back and view the universe from the largest possible scale, you would see that it's not randomly scattered with galaxies. Instead, you would see an intricate web of structure, galaxies clustered together in groups and clusters, these clusters connected by filaments of matter, with vast empty voids in between. It looks remarkably like a three-dimensional spiderweb, with galaxies strung along the threads and enormous empty spaces in between. This cosmic web, as astronomers call it, is gravity's greatest masterpiece. It's the result of billions of years of gravitational evolution, as tiny variations in the density of matter in the early universe grew and evolved under the influence of gravity, eventually becoming the galaxies and galaxy clusters we see today. Imagine the universe shortly after the Big Bang, when it was much smaller, much denser, and much more uniform than it is today. But it wasn't perfectly uniform. There were tiny fluctuations, regions that were slightly denser than average, and regions that were slightly less dense. These fluctuations were incredibly small, variations of only about 1 part in 100,000. But gravity is patient and persistent. Over millions and billions of years, these tiny density variations grew. The slightly denser regions attracted more matter, becoming even denser, while the slightly less dense regions lost matter to their denser neighbors, becoming even emptier. It's like a cosmic version of the rich getting richer and the poor getting poorer, except the currency is matter and energy, and the economic system is governed by the laws of gravity. The result is the cosmic web we see today, a universe where matter is organized into an intricate network of filaments and clusters, with most of the volume consisting of vast, nearly empty voids. It's as if gravity has been playing a cosmic game of connect the dots for billions of years, linking matter together along the paths of least resistance through the curved landscape of space-time, and this structure is still evolving. Galaxy clusters are still growing, still accreting matter from their surroundings. Galaxies are still merging, still being shaped by the gravitational tug-of-war between their neighbors. Our own Milky Way is on a collision course with the Andromeda Galaxy, our nearest large neighbor, and in about 4.5 billion years, they'll merge into a single, larger galaxy. But gravity's influence extends even beyond the visible matter we can see. Most of the matter in the universe is actually invisible. Dark matter, which interacts gravitationally but doesn't emit or absorb light. We know it's there because we can see its gravitational effects on the visible matter, but we can't observe it directly. It's like trying to understand a dance by watching only some of the dancers. You can infer the presence of the invisible partners from the movements of the visible ones. This dark matter makes up about 85% of all matter in the universe, and it's the dominant force in shaping the cosmic web. The visible galaxies we see are actually just the bright centers of much larger dark matter halos, invisible structures that can extend far beyond the visible boundaries of the galaxies themselves. And then there's dark energy, even more mysterious than dark matter. While gravity tends to pull things together, dark energy seems to be pushing space itself apart, causing the expansion of the universe to accelerate. It's as if there's a cosmic tug-of-war between gravity, trying to pull everything together, and dark energy, trying to push everything apart. The ultimate fate of the universe depends on which force wins this cosmic battle. If gravity eventually overcomes dark energy, the universe might someday stop expanding and begin contracting, eventually collapsing back into a big crunch. If dark energy continues to dominate, the universe will expand forever, growing colder and emptier as the galaxies drift apart. But, for now, in this cosmic moment we call the present, gravity continues to shape the universe on the largest scales. It's the architect of cosmic structure, the force that turns a nearly uniform early universe into the rich, complex, beautiful cosmos we see today. Every galaxy, every cluster, every filament of the cosmic web is a testament to gravity's patient, persistent work over billions of years. As you rest here, perhaps feeling drowsy, remember that you're part of this grand cosmic structure. The atoms in your body were forged in the hearts of stars. Stars that were born in galaxies held together by gravity, galaxies that are part of the vast cosmic web that gravity has woven over the history of the universe. You're not just resting on Earth, you're resting in the cosmic web itself, a tiny but essential part of the larger structure in the universe. There's something deeply unsettling about the realization that most of the universe is invisible. We look up at the night sky and see stars and galaxies, and we assume that what we see is what there is. But astronomers have discovered something that challenges this fundamental assumption. The universe is full of matter we can't see. Matter that makes itself known only through its gravitational effects. This invisible matter, dark matter, makes up about 85% of all matter in the universe. It's not made of atoms like the matter we're familiar with. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. It's like a cosmic ghost, present everywhere but invisible to all our traditional methods of observation. The first hints of dark matter came from observations of galaxy clusters in the 1930s. Astronomer Fritz Zwicky was studying the Coma cluster, a group of galaxies bound together by gravity, and he noticed something strange. The galaxies in the cluster were moving much faster than they should have been if they were held together only by the gravity of the visible matter. It was as if the cluster contained far more mass than could be accounted for by the stars and gas that astronomers could see. For decades, this observation was largely ignored or dismissed. But as observations improved and multiplied, The evidence for dark matter became overwhelming. Galaxy after galaxy, cluster after cluster, showed the same pattern. There was far more gravitational influence than could be explained by visible matter alone. The most compelling evidence comes from the rotation curves of galaxies. When astronomers measure how fast stars orbit around the centers of galaxies, they find something unexpected. According to Newton's laws, stars farther from the galactic center should orbit more slowly, just as planets farther from the Sun orbit more slowly. But that's not what we observe. Instead, stars at the edges of galaxies orbit at roughly the same speed as stars closer to the center. It's as if the galaxy is embedded in a much larger, invisible halo of matter, a halo that extends far beyond the visible boundaries of the galaxy itself. This dark matter halo provides the extra gravitational pull needed to keep the outer stars moving at their observed speeds. Imagine you're watching a figure skater spinning on ice. When the skater pulls their arms in close to their body, they spin faster. When they extend their arms, they spin more slowly. This is exactly what we'd expect to see in galaxies if they contained only visible matter. Stars farther from the center should move more slowly, but instead, it's as if the skater is somehow maintaining the same spinning speed regardless of how far their arms are extended. The implications are staggering. If dark matter makes up 85% of all matter, then everything we can see, stars, planets, gas clouds, even ourselves, represents only a tiny fraction of what actually exists. We're living in a universe dominated by invisible matter, matter that shapes the formation and evolution of galaxies but remains completely hidden from our direct observation. This invisible matter isn't uniformly distributed throughout the universe. Computer simulations suggest that it forms a complex web of filaments and halos, with visible matter falling into the gravitational wells created by dark matter concentrations. In this view, visible galaxies are like bright lights scattered throughout a vast, invisible scaffolding of dark matter. But what is dark matter made of? This is one of the greatest mysteries in modern physics. It's not made of ordinary atoms. If it were, we'd be able to see it. It's not antimatter. Antimatter would annihilate with ordinary matter, producing detectable radiation. It's not black holes. There simply aren't enough of them to account for all the missing mass. The leading candidates are exotic particles that interact only gravitationally, particles that were produced in the early universe, but have remained largely invisible ever since. These hypothetical particles would pass through ordinary matter like ghosts, interacting only through their gravitational effects. They could be streaming through your body right now, trillions of them every second, without your ever knowing it. Scientists around the world are trying to detect these particles directly, using incredibly sensitive detectors buried deep underground to shield them from other forms of radiation. So far, these experiments have come up empty, but the search continues. The discovery of dark matter particles would be one of the most profound breakthroughs in the history of physics. But there's another possibility, one that's even more radical. What if dark matter doesn't exist at all? What if our understanding of gravity itself is incomplete? Some physicists have proposed that gravity might behave differently on very large scales, creating the illusion of invisible matter when none actually exists. This alternative theory, called modified Newtonian dynamics or MOND, suggests that Newton's law of gravity breaks down when gravitational accelerations become very small, exactly the conditions that exist at the edges of galaxies. If gravity becomes stronger than Newton predicted at these scales, it could explain the rotation curves of galaxies without requiring any invisible matter. The debate between dark matter and modified gravity is one of the most active areas in modern astrophysics. Both theories can explain many observations, but neither can explain everything. The universe, it seems, is more complex and mysterious than either simple explanation can accommodate. As you rest here, perhaps feeling the familiar weight of your body against the bed or chair, remember that you're surrounded by mystery. If dark matter exists, it's streaming through you right now. Invisible particles that interact with ordinary matter only through gravity. If modified gravity is correct, then the force that keeps you grounded operates by different rules on cosmic scales than it does here on Earth. Either way, you're part of a universe that's far stranger and more wonderful than our everyday experience suggests. The gravity that holds you to the Earth, that keeps the moon in its orbit, that shapes the structure of galaxies, it's all part of a cosmic mystery that we're only beginning to understand. There's a battle happening in the cosmos, a fundamental conflict between two opposing forces that will determine the ultimate fate of everything that exists. On one side is gravity, the force that has spent billions of years patiently gathering matter together, building stars and galaxies, and the intricate cosmic web that spans the universe. On the other side is something even more mysterious: dark energy, a force that seems to be pushing space itself apart, causing the expansion of the universe to accelerate. This cosmic tug-of-war was discovered almost by accident. In the 1990s, astronomers were studying distant supernovae, exploding stars that serve as cosmic lighthouses, allowing us to measure distances across the universe. They expected to find that the expansion of the universe was slowing down, gradually decelerating under the influence of gravity. Instead, they discovered something shocking. The expansion was speeding up. It was as if they had thrown a ball into the air and watched it accelerate upward instead of falling back down. The discovery was so unexpected that both teams of astronomers who made it initially suspected they had made an error. But repeated observations confirmed the impossible. The universe is not only expanding but expanding at an accelerating rate. This acceleration implies the existence of something that acts like a repulsive force on cosmic scales, something that pushes space apart rather than pulling it together. Physicists call this mysterious influence dark energy, and it appears to make up about 70% of the total energy content of the universe, combined with dark matter, which makes up about 25%. Ordinary matter, the stuff we can see and touch, represents less than 5% of the cosmos. Think about that for a moment. The universe is dominated by two forms of dark components that we can't directly observe. Dark matter reveals itself through its gravitational effects on visible matter, while dark energy reveals itself through its effects on the expansion of space itself. We live in a universe that is mostly invisible, mostly mysterious, mostly beyond our direct experience. The nature of dark energy is one of the deepest puzzles in modern physics. It could be a property of space itself, a cosmological constant that represents the energy density of empty space. In this view, even a perfect vacuum has a small but positive energy density, and as space expands, more vacuum is created, leading to more dark energy and therefore more acceleration. Alternatively, dark energy could be a dynamic field that changes over time, something like the Higgs field that gives particles their mass, but operating on cosmic scales. If this is the case, the amount of dark energy in the universe could change over time, potentially leading to phases of acceleration and deceleration in the cosmic expansion. The implications of dark energy are profound. If it continues to dominate the expansion of the universe, galaxies will drift apart at ever-increasing speeds. Eventually they will be so far apart that light from one galaxy will never reach another. The universe will become a cold, dark, empty place, with isolated galaxies like islands in an infinite sea of space. But there's another possibility. What if dark energy is not constant over time? What if it eventually weakens or even reverses? In that case, gravity might eventually win the cosmic tug-of-war, causing the expansion to slow down, stop, and then reverse. The universe would begin to contract, eventually collapsing back into a big crunch, the opposite of the Big Bang. Or perhaps the nature of dark energy will change in ways we can't yet predict. Some theories suggest that dark energy could become even more dominant, eventually overwhelming not just gravity but all the other forces of nature. In this scenario, called the Big Rip, the acceleration of space would become so extreme that it would tear apart galaxies, then solar systems, then planets, then molecules, then atoms themselves. The universe would end in a frenzy of destruction, as accelerating space rips apart the very fabric of matter. But these are distant concerns. For now, in this cosmic moment we call the present, the battle between gravity and dark energy continues. On small scales, within galaxies, within solar systems, within our daily lives, gravity dominates. It holds us to the Earth, keeps the moon in its orbit, binds the stars together in galaxies. Dark energy only makes itself felt on the largest scales, where its gentle but persistent push gradually separates galaxy clusters from one another. It's a strange and beautiful universe we live in, where the force that keeps our feet on the ground is locked in a cosmic battle with an invisible energy that's pushing space itself apart. The outcome of this battle will determine whether the universe ends in ice or fire, in eternal expansion or ultimate collapse, in the slow heat death of maximum entropy or the violent destruction of accelerating space. As you rest here, feeling the familiar pull of gravity keeping you grounded, remember that you're witnessing one side of the greatest conflict in the cosmos. The same force that holds you to the Earth is engaged in a struggle with dark energy that will determine the fate of everything that exists. It's a battle being fought on scales so vast that we can barely comprehend them, yet its outcome will ultimately affect every atom in your body, every star in the sky, every galaxy in the observable universe. For now, gravity and dark energy exist in a delicate balance, each dominating in its own domain, but that balance is slowly shifting, and in the deep future, one or the other will emerge victorious. The universe is not a static place. It's a dynamic arena where fundamental forces compete for dominance, and we're fortunate to be living in an epoch when that competition has created the rich, complex cosmos we see around us. There's a simple experiment you can do right now. If you happen to have two objects of different weights nearby, pick them up, perhaps a book and a pen, or a coin and a piece of paper. Hold them at the same height, and drop them simultaneously. What happens? If you're dropping them in air, the lighter object might fall more slowly due to air resistance. But if you could somehow eliminate air resistance, if you could drop them in a perfect vacuum, something remarkable would happen. They would hit the ground at exactly the same time regardless of their weights. This seems almost magical, doesn't it? Our everyday experience suggests that heavier objects should fall faster than lighter ones. After all, if you're pulling two objects with your hands, the heavier one requires more force to accelerate. But gravity doesn't work that way. In the absence of air resistance, a feather falls at exactly the same rate as a hammer. A grain of sand falls at exactly the same rate as a boulder. This counterintuitive fact was first demonstrated by Galileo in the early 1600s, though probably not by dropping objects from the Leaning Tower of Pisa, as legend suggests. Galileo realized that the rate of fall depends not on the weight of an object, but on the strength of the gravitational field it's falling through. On Earth, everything falls with the same acceleration, about 32 feet per second squared, regardless of its mass. But why should this be true? It's not obvious from our everyday experience with forces. When you push a shopping cart, you need more force to accelerate a full cart than an empty one. When you throw a ball, you need more force to accelerate a heavy ball than a light one. So why doesn't gravity work the same way? The answer lies in a deep and beautiful symmetry in the laws of physics. Every object has two different types of mass: inertial mass and gravitational mass. Inertial mass is the property that determines how hard it is to accelerate an object. The more inertial mass something has, the more force you need to speed it up or slow it down. Gravitational mass is the property that determines how strongly an object responds to gravity. The more gravitational mass something has, the stronger the gravitational force acting on it. Now here's the remarkable thing. These two types of mass are always exactly equal to each other. An object that's twice as hard to accelerate, twice the inertial mass, also experiences twice the gravitational force, twice the gravitational mass. The two effects cancel out exactly, which is why everything falls at the same rate. This equivalence of inertial and gravitational mass is not something we can derive from more fundamental principles. It's an empirical fact about the universe, something we discover through observation and measurement. But it's such a fundamental and precise equivalence that it hints at something deeper about the nature of gravity itself. Einstein recognized this equivalence as a profound clue about the nature of reality. He called it the equivalence principle, and it became the foundation of his general theory of relativity. If inertial mass and gravitational mass are exactly equal, Einstein reasoned, then gravity and acceleration are fundamentally indistinguishable phenomena. Think about it this way. If you're in a windowless room, and you feel yourself pressed against the floor, how would you know whether you're standing in a gravitational field or accelerating upward through empty space? According to the equivalence principle, there's no experiment you could perform inside that room that would tell you the difference. Gravity and acceleration are two sides of the same coin. This insight led Einstein to his revolutionary understanding of gravity as curved space-time. If gravity and acceleration are equivalent, and if acceleration is just motion through space and time, then gravity must be a property of space and time themselves. Objects don't fall because they're being pulled by a force. They fall because they're following the straightest possible paths through space-time that has been curved by the presence of mass and energy. The equivalence principle also explains why everything falls at the same rate. In Einstein's universe, falling objects aren't being accelerated by a force, they're following their natural paths through curved space-time. And those natural paths, those geodesics, are the same for all objects regardless of their mass. A feather and a hammer both follow the same geodesic through curved space-time, which is why they fall at the same rate in a vacuum. This principle has been tested with extraordinary precision. Modern experiments can measure the acceleration of different materials, aluminum, titanium, beryllium, and verify that they all fall at exactly the same rate to within a few parts in a trillion. The equivalence principle is one of the most precisely verified principles in all of physics, but the implications go far beyond falling objects. The equivalence principle tells us that there's no fundamental difference between being at rest in a gravitational field and being accelerated through empty space. This means that many of the strange effects of gravity, time dilation, length contraction, the bending of light, are actually just consequences of acceleration and can be understood without invoking the complexities of curved spacetime. As you rest here, perhaps feeling the familiar weight of your body, remember that you're experiencing the equivalence principle directly. The sensation of weight you feel is indistinguishable from the sensation you would feel if you were accelerating upward through empty space. Your body can't tell the difference between being pulled by gravity and being pushed by acceleration. And if you were to drop something right now, it would fall at exactly the same rate as anything else you might drop, regardless of its weight or composition. This isn't because gravity is pulling all objects with the same force. It's because all objects are following the same natural paths through the curved spacetime created by the Earth's mass. The equivalence principle reveals that gravity is not a force at all, but a manifestation of the geometry of spacetime itself. There's something deeply appealing about the idea of anti-gravity, isn't there? The dream of cancelling out gravity's pull, of floating effortlessly through the air, of building vehicles that can hover and glide without wings or propellers. It's a dream that appears in countless science fiction stories, from H.G. Wells' The First Men in the Moon, to the floating cities of Star Wars. But is it possible? Could we ever find a way to shield ourselves from gravity, or create a repulsive gravitational force? The short answer, unfortunately, is probably not, at least not in the way most people imagine. Gravity is fundamentally different from the other forces of nature. Here's something wonderful and strange. That feeling you have, that sense of weight pressing you into your chair or bed right now, isn't actually gravity pulling you down. It's something far more beautiful and mysterious than that. Imagine, if you will, that you're not sitting still at all. Imagine that you're actually falling right now, this very moment, through space and time, following the most natural path possible through the universe. But the ground beneath you, the chair you're sitting in, the bed you're lying on, they're all pushing up against you, interfering with your natural fall through the curved landscape of space-time itself. This is Einstein's gentle revolution, whispered to us more than a century ago. Gravity isn't a force pulling you down, it's the shape of space and time itself, curved and bent by the presence of mass and energy. You're not being pulled toward the Earth. You're following the straightest possible path, through a universe that's been gently warped by our planet's presence. Think of it like this. Imagine you're walking across a vast trampoline, perfectly flat and tight. Your steps are straight and true, but now imagine someone places a heavy bowling ball in the center of that trampoline. The fabric dips and curves, creating hills and valleys in what was once flat. Now, when you try to walk in a straight line, you find yourself naturally rolling toward the bowling ball. Not because it's pulling you, but because the very surface you're walking on has been reshaped. This is what mass does to spacetime. The sun doesn't pull the planets toward it. It curves the fabric of spacetime so dramatically that planets, following their natural straight-line paths, end up orbiting in great sweeping circles. The Earth doesn't pull the moon toward it. It creates a gentle depression in spacetime that the moon rolls around, like a marble circling the rim of a funnel. And you, right now, are following that same natural path, falling freely through Einstein's curved universe. It's only the solid matter beneath you that creates the sensation of weight, pushing up against your natural trajectory through spacetime. In a way, you're always falling, and the ground is always catching you, moment by moment, creating that familiar feeling of being pressed down that we call weight. Isn't it wonderful? The most fundamental experience of your physical existence, the feeling of gravity, is actually the universe's way of showing you that space and time themselves are alive, flexible, responsive to the presence of matter and energy. Every step you take, every breath you breathe, every moment you spend resting here, you're participating in a cosmic dance between matter and the very fabric of reality itself. Picture, if you will, a place where gravity becomes so intense that not even light can escape. This is the realm of black holes, cosmic shadows that dance at the extreme limits of what we know about the universe. Imagine standing near a black hole, though of course you'd never survive the experience. As you approach what scientists call the event horizon, that invisible boundary of no return, something extraordinary happens to time itself. From your perspective, everything feels normal, but to someone watching from a safe distance, you would appear to slow down, your movements becoming more and more languid, like a film gradually winding down to a stop. This isn't science fiction, it's the beautiful, strange reality of how gravity warps the very fabric of time. Einstein showed us that space and time are woven together like a cosmic tapestry, and gravity is simply the curvature of this fabric. Near a black hole, that curvature becomes so extreme that time itself bends like light through a lens. But here's where it gets even more mysterious. At the center of a black hole lies what we call a singularity, a point where our understanding of physics simply stops. It's like reaching the edge of a map where medieval cartographers once wrote, "Here be dragons." The mathematics that usually guide us through the universe break down completely, whispering secrets we're not yet ready to hear. What's fascinating is that black holes aren't cosmic vacuum cleaners. Despite their fearsome reputation, they're more like cosmic whirlpools, creating elegant spirals of matter and energy as they feed. The gravity is so intense that it heats in falling material to millions of degrees, creating some of the brightest objects in the universe. It's a paradox that appeals to the poet in all of us. The darkest objects creating the most brilliant light. These cosmic shadows also do something that seems impossible. They evaporate. Stephen Hawking discovered that black holes slowly leak away their mass through a process so subtle it would take longer than the age of the universe for most black holes to disappear completely. It's as if the universe has a sense of cosmic justice, ensuring that even the most powerful gravitational prisons eventually set their captives free. And perhaps most mysteriously of all, black holes seem to store information on their surfaces, like cosmic hard drives written in the language of spacetime itself. This discovery has revolutionized our understanding of how information behaves in the universe, suggesting that gravity might be far more fundamental to reality than we ever imagined. Now, let's venture into the heart of a beautiful puzzle that has kept physicists awake at night for nearly a century. We have two magnificent theories that describe our universe: Einstein's general relativity, which explains gravity as the curvature of spacetime, and quantum mechanics, which governs the behavior of the smallest particles. Both are spectacularly successful in their own domains, yet they seem to speak entirely different languages. It's like having two exquisite pieces of music that sound perfect when played separately, but create discord when you try to play them together. General relativity works beautifully for planets, stars, and galaxies, the grand cosmic symphony of large-scale structures. Quantum mechanics governs atoms, electrons, and photons with remarkable precision. But when you try to apply quantum mechanics to gravity itself, the mathematics become, well, unruly. The problem becomes acute when we try to understand what happens at the very beginning of the universe, in those first fractions of a second after the Big Bang, when everything was compressed into a space smaller than a proton. Here, gravity would have been as strong as the other fundamental forces, and we need a theory that can handle both the quantum world and the gravitational world simultaneously. Imagine trying to describe a raindrop using only the language of geology, or explaining a mountain using only the vocabulary of meteorology. That's somewhat like what we're trying to do when we attempt to merge these two theories. Each approach reveals different aspects of reality, but neither gives us the complete picture. This incompatibility isn't just an academic curiosity. It points to something profound about the nature of reality itself. Perhaps gravity isn't a force at all, but rather an emergent property of something deeper. Or maybe our understanding of space and time needs to be fundamentally revised. Some physicists have suggested that space itself might be granular at the smallest scales, made up of discrete units like pixels on a cosmic screen. The search for a unified theory has led to some of the most beautiful and strange ideas in physics. String theory suggests that the fundamental building blocks of reality might be tiny vibrating strings, each note in their cosmic symphony corresponding to a different particle. Luke quantum gravity proposes that space itself has a fabric, a weave so fine that it only becomes apparent at scales a trillion times smaller than a proton. What's particularly humbling is that this puzzle reminds us how much we still don't know. We've mapped the human genome, split the atom, and sent spacecraft to the edge of the solar system, yet the most familiar force in our daily lives, the one that holds us to Earth, remains fundamentally mysterious at its deepest level. Let's drift now into the realm of the incredibly small, where space and time themselves might whisper secrets that could reshape our understanding of gravity. At the quantum level, the smooth fabric of space-time that Einstein described might be far more intricate than we ever imagined. Picture space-time not as a smooth sheet, but as a cosmic fabric woven from threads too small to see. At the smallest possible scale, what physicists call the Planck length, about a trillionth of a trillionth of a trillionth of a meter, space itself might be granular, made up of discrete units like atoms of geometry. This is the domain of loop quantum gravity, a theory that suggests space has a texture, a fundamental granularity that becomes apparent only at scales so small that comparing them to everyday objects is like comparing a single atom to the entire observable universe. At these scales, the smooth curves of Einstein's spacetime might give way to a quantum foam of constantly fluctuating geometry. Imagine if you could zoom into a photograph far enough to see the individual pixels, and then zoom further to see that each pixel is actually made of smaller pixels and so on. Loop quantum gravity suggests that if we could zoom into the fabric of space itself, we might eventually reach a fundamental scale where space is quantized, where there's a smallest possible unit of volume, just as there's a smallest possible unit of energy. String theory offers a different whisper from the quantum realm. It proposes that the fundamental constituents of reality aren't point particles, but tiny vibrating strings. These strings are so small that even if we could magnify a proton to the size of the solar system, a string would still be too small to see. Yet these invisible threads might be the source of all the forces in nature, including gravity. In string theory, gravity emerges from the vibrations of these cosmic strings, like different notes on an instrument that's far too small to hear. The graviton, the hypothetical particle that carries the gravitational force, would be one particular mode of string vibration, no different in principle from the photon that carries light or the electron that flows through circuits. But here's where it gets truly mystical. String theory requires extra dimensions beyond the three of space and one of time that we experience. These additional dimensions might be curled up so tightly that they're invisible to us, existing at every point in space yet remaining hidden from our perception. Gravity, unlike the other forces, might be able to leak into these extra dimensions, which could explain why it's so much weaker than electromagnetism or the strong nuclear force. Both theories whisper of a reality far stranger and more beautiful than our everyday experience suggests. They hint that space and time, the very stage upon which all cosmic drama unfolds, might themselves be emergent properties of something even more fundamental. It's as if we've been watching shadows on the wall of Plato's cave, and these theories are our first glimpses of the fire that casts those shadows. Now we venture into perhaps the most mind-bending territory of all, the possibility that gravity itself might emerge from something as abstract as information. This isn't science fiction, it's a serious proposal that's reshaping how physicists think about the fundamental nature of reality. The journey begins with a discovery that seemed almost too strange to be true. In the 1970s, physicists realized that black holes have a temperature and emit radiation. But more mysteriously, they found that the amount of information a black hole can contain is proportional not to its volume, but to the area of its surface, its event horizon. This led to what's called the holographic principle, the radical idea that all the information contained within a volume of space can be encoded on its boundary, like a hologram that appears three-dimensional but is actually stored on a two-dimensional surface. It's as if the universe we experience in 3 dimensions might actually be a projection from information stored on a distant two-dimensional surface. But the implications go much deeper. Some physicists now suggest that gravity itself might be what they call an emergent phenomenon. Not a fundamental force, but rather something that arises from the collective behavior of vast amounts of quantum information, like the way temperature emerges from the motion of countless individual atoms. Imagine a vast library where information is constantly being processed, shared, and organized. The flow of information through this library creates patterns and structures, much like the flow of water creates whirlpools and currents. In this analogy, gravity might be like the circulation patterns that naturally emerge from the library's information processing, not a separate force, but a consequence of how information moves and organizes itself. This perspective suggests that what we call the fabric of spacetime might actually be woven from quantum entanglement, the mysterious connection that can exist between particles even when they're separated by vast distances. When particles become entangled, they share information instantaneously, regardless of the space between them. Some theories propose that the geometry of spacetime itself emerges from the pattern of these quantum connections. It's a beautiful and humbling idea, that the force holding planets in orbit, the curve of light around stars, and the very structure of the universe itself might all arise from the way information organizes and flows in the quantum realm. It suggests that reality is far more interconnected than we might have imagined, with information serving as the fundamental currency of existence. This approach has already yielded insights into some of the deepest puzzles in physics, including the information paradox of black holes and the nature of dark energy. It hints that by understanding how information behaves in the quantum world, we might finally bridge the gap between general relativity and quantum mechanics. Perhaps most poetically, it suggests that the universe might be, in a very real sense, a kind of cosmic computer, not in the mechanical sense of circuits and processes, but in the deeper sense of a system that processes and organizes information at the most fundamental level. And we, as conscious beings capable of thought and memory, might be brief, beautiful patterns in this cosmic information flow. Let's take a gentler journey now, imagining what it would feel like to experience gravity's embrace on other worlds. Each planet and moon in our solar system offers a unique gravitational signature, a different way of being held by the cosmos. On the moon, you would weigh only 1/6 of what you weigh on Earth. Walking would become a kind of graceful dance, with each step launching you in a gentle art. The Apollo astronauts described it as feeling like they were moving through water, with a dreamlike quality where even the simplest movements became poetic. Your coffee would pour in a thin, precise stream, and a dropped feather would fall so slowly you could watch it drift like a leaf in an autumn breeze. Jupiter, that gentle giant, would tell a different story entirely. Its gravity is more than twice Earth's, so walking would feel like carrying an invisible backpack filled with stones. Each step would be deliberate, each movement considered. But Jupiter has no solid surface to walk on. It's a world of swirling gases and storms that have raged for centuries. If you could somehow stand on its cloud tops, you'd feel the crushing weight of a gravitational field that dominates the entire outer solar system. Mars offers a middle ground, gravity about 38% of Earth's strength. Here you could leap nearly 3 times as high as on Earth, yet still feel grounded enough to walk normally. The red planet's gravity is strong enough to hold an atmosphere, though a thin one, and to shape landscapes with familiar-looking river valleys and polar ice caps. It's a world where Earth life might feel just different enough to be exotic, yet familiar enough to feel like home. On tiny Pluto, so far from the Sun that it was demoted from planetary status, gravity is only about 6% of Earth's. Here you could throw a baseball and watch it sail in a long, lazy arc that would take minutes to complete. The horizon would curve more noticeably, reminding you that you're standing on a world smaller than Earth's moon. In a realm where the sun appears as just a bright star in the perpetual twilight sky. But perhaps the most fascinating gravitational environment would be aboard the International Space Station, where astronauts experience what we call microgravity. They're not beyond Earth's gravitational pull, they're actually falling toward our planet constantly, but moving forward so fast that they keep missing it. It's a perpetual state of free fall, where water forms perfect spheres that float in the air, and tears don't roll down your cheeks but form small bubbles that cling to your eyes. Each of these worlds reminds us that gravity isn't just a force, it's a sculptor of possibilities. It determines whether a world can hold an atmosphere, whether water can exist in liquid form, whether mountains can grow tall or are flattened by their own weight. It influences the pace of life itself, from the rhythm of tides to the circulation of blood in our bodies. These alien gravities also remind us how perfectly tuned our own world is. Earth's gravity is strong enough to hold a rich atmosphere and vast oceans, yet gentle enough to allow life to flourish. It's neither the crushing weight of Jupiter, nor the barely there whisper of the moon, but something perfectly in between, a gravitational Goldilocks zone that has allowed billions of years of evolution to unfold. And so we return to our central question. Having journeyed through black holes and quantum foam, through the mathematics of curved spacetime, and the possibility that reality itself might be made of information, what is gravity, really? The honest answer, the one that might surprise you, is that we still don't fully know. After centuries of study, from Newton's apple to Einstein's equations, to the latest theories of quantum gravity, this most familiar of forces remains beautifully mysterious. What we do know is extraordinary. We know that gravity isn't really a force in the traditional sense, but rather the curvature of space-time itself. We know that it can slow down time, bend light, and create regions of space where the normal rules of physics break down. We know that it operates on scales from the quantum to the cosmic, shaping everything from the formation of atoms to the evolution of galaxies. But perhaps what's most beautiful about gravity is how it connects everything. Right now, as you listen to these words, you're part of a vast gravitational dance. The moon is pulling on the water in your body, just as it pulls on the oceans. The sun is holding you in its gravitational embrace, keeping Earth in its orbit. Even the center of our galaxy, with its supermassive black hole, is tugging gently on every atom in your body. This connection runs deeper than mere physics. Gravity is the reason stars form and burn, creating the heavy elements that make up our bodies. It's the reason planets coalesce from cosmic dust, creating the worlds where life can emerge. In a very real sense, gravity is the cosmic gardener, creating the conditions for complexity, beauty, and consciousness to flourish. The fact that we don't fully understand gravity might be its greatest gift to us. It reminds us that the universe is far stranger and more wonderful than we often imagine. It keeps us humble, curious, and filled with wonder. Every time we think we've figured it out, gravity whispers new secrets that send us back to the drawing board, armed with new questions and fresh sense of awe. Perhaps gravity's deepest truth is that it embodies the fundamental interconnectedness of all things. In Einstein's vision, there is no empty space, only the curved geometry of spacetime, connecting every point in the universe to every other point. We are not separate from the cosmos, but part of its very fabric, woven into the same gravitational tapestry that binds quarks and galaxies alike. So as you drift towards sleep tonight, carried by the gentle pull of gravity into dreams, remember that you're participating in something magnificent and mysterious. You're part of a cosmic dance that began with the Big Bang and will continue long after the last star burns out. You're held by the same force that shapes galaxies and guides the light from distant stars to your eyes. What is gravity really? Perhaps it's the universe's way of ensuring that nothing, no star, no planet, no person, is ever truly alone. It's the cosmic embrace that connects us all, the invisible thread that weaves the tapestry of existence. And in that embrace, we find not just the secret of falling objects and orbiting planets, but a deeper truth about the fundamental unity of all things. Sleep well, fellow traveler in spacetime. Gravity has you, and always will.